Welcome to the Unit 11 Test Remediation Guided Practice. Starting with some academic vocabulary, we need to define the following terms. Chemical potential energy is energy that is stored in chemical bonds. Kinetic energy is the energy of movement. Thermal energy is the internal energy of an object. Temperature is the measure of the average kinetic energy of a system. Heat is the transfer of energy between two objects of different temperatures from high to low. Thermal equilibrium, and so thermal equilibrium is when objects of different energies collide and become the same temperature. Fusion is the transition from a liquid to a solid. Melting is the transition from a solid to a liquid. Condensation is the transition from a liquid to a gas. From a gas to a liquid. Vaporization is the transition from a liquid to a gas. Sublimation is a transition from a solid straight to a gas. Crystal lattice formation is a transition from a gas straight to a solid. Critical point. The critical point is the temperature and pressure at which a liquid and gas are indistinguishable. The triple point is the temperature and pressure at which solid, liquid, and gas exists for a pure substance. Specific heat capacity is the measure of the energy required to change 1 kilogram of an object 1 degree Celsius. An endothermic reaction is a reaction that absorbs energy. An exothermic reaction is a reaction that releases energy. Enthalpy is the change in heat per mole. And Hess's law is the change in enthalpy overall is the sum for all the individual changes. So 0 Kelvin, to get it to Celsius, we just subtract 273. And 0 minus 273 gives us negative 273 degrees Celsius. And then to go to Fahrenheit, we use the equation Fahrenheit equals our Celsius temperature, which is negative 273, times 9/5 plus 32. And we get a negative 459.4 degrees Fahrenheit. Next, it says convert 100,000 joules to dietary calories. A dietary calorie is a kilocalorie. So we have 100,000 joules, and there are 4,184 joules in one capital C dietary calorie, which is 23.9 kilocalories. C, it says, which way will heat be transferred? Heat is always transferred from hot to cold. What are the standard units of heat and temperature? Heat is measured in joules, and temperature is measured in degrees Celsius. And we use Kelvin. E, what is the difference between heat and temperature? Heat is the total energy of a system. Temperature is the measure of the average kinetic energy in a system. Looking at specific heat. So when working with specific heat, we're using the equation Q equals mc delta T. And so we have our specific heat capacities. Pay attention to our unit here is joules kilograms degrees Celsius. And so it's of different substances. And it says, what is the mass of copper when the temperature increases by 5 degrees when subjected to 2.8 times 10 to the 8th joules of energy? And so we're solving for mass using Q equals mc delta T. So we're solving for M. So what we will get is M equals Q all over C delta T. So what we get is Q is 2.8 times 10 to the 8th joules all over our specific heat. It's of copper, so we look up here. There's copper. There's its specific heat. So 3.8 times 10 to the second. And then we have temperature. And it's change in temperature. So it increased by 5. So our change in temperature is going to be 5 degrees Celsius. And so we go ahead, multiply the bottom, divide the top by the bottom, and we will get a mass, a very large mass of 147,368. And since this unit is in joules kilogram degrees Celsius, this is going to be kilograms. B, it says a 250 gram sample of ethyl alcohol is initially at 10 degrees Celsius and subjected to 20,000 joules. What is the final temperature? So using our equation, Q equals mc delta T means temperature final minus temperature initial. So our initial temperature is going to be 10. Our joules is going to go right here. Our mass is 250 grams, and since this is ethyl alcohol, we come up here, we find it, there's its specific heat, and we would plug that into C. Now remember that our unit for specific heat is joules kilograms, so this 250 grams need to be converted to kilogram, which is 0.25 kilograms. Plug all those variables in and then solve for delta or the temperature final, and we should get a final temperature of 42.5 degrees Celsius. And it says C is which of the following is the best insulator material. When we're looking at an insulator, we want something with a very high specific heat, and so the best one, the highest, would be our water, which is 4.18 times 10 to the third. Phases of matter. So we're looking at phase changes. It says calculate the energy required to take 1.2 kilograms of 0 degree Celsius lead into 1500 degrees Celsius lead. And so when we're looking at this, we're going to use two equations. We're going to use our Q equals mc delta T. We know to use this equation when temperature changes. And temperature is going to change here. And we're also going to use Q equals mL, which this is our mass times our latent heat of either fusion or vaporization. Because what our graph is going to do is our lead is going to start off at 0 degrees, and then our lead is going to go up to 327.5, and then it's going to plateau out. Well, that plateau is where it's changing phase. We use the Q equals mL when there's no temperature change, and then it's going to go up again to 1500 degrees, which is just below boiling point, and so we'll use the Q equals mc delta T. So we're going to use this equation twice, once there and once there, and we'll use the Q equals mL when it just is changing phase. So our first one is going to be our Q equals mc delta T, and so our Q equals a mass of 1.2 kilograms, and this is in kilograms, times the specific heat, which I got from the previous our previous chart, which is 1.3 times 10 to the second, times our change in temperature. So its initial temperature is 0, its final temperature is 327.5, so our change in temperature is 327.5 minus 0. And we get an initial increase of 51,090 joules of energy. And then once it reaches 327.5, it's going to change phase. And we're going to use the Q equals mL. And so all we do is we take our Q Q equals our mass, which is 1.2 kilograms, times our our latent heat of fusion, which for lead is going to be 2.5 times 10 to the fourth, which this gives us a Q value of 30,000 joules. And then it's going to change temperature again, so we're going to use the Q equals MC delta T. So Q equals M, which is 1.2 kilograms. Our our specific heat, which is going to be 1.3 times 10 to the second, times our change in temperature. It's going to go all the way up to 1500 degrees. So from 327.5 to 1500. And we take that, and that is going to be 1172.5. And we multiply those together, and we get a Q value of 1,829,100 joules. And all we do is add all of these Q values together, and we get the amount of energy that it took, which would be 1910190 joules of energy. Calculate the energy required to melt 125 kilograms of gold initially at 2856 degrees Celsius. Since the melting point of gold is 2856, you're only going to use a Q equals ml. You should get an answer of 1.375 times 10 to the 8th joules. C, it says draw the carbon dioxide at -80 and 0 degrees Celsius. So we're looking at carbon dioxide. -80 means that it's going to be a solid, and then 0 degrees Celsius means that it will go ahead and be boiling, and so it'll be gas. So solid, it will be tightly packed together, and then as a gas, they'll be all over the place. Moving on to Hess's Law. It says calculate the delta H for the reaction of, we see methane reacting with ammonia to produce hydrocyanic acid and hydrogen gas. Now, when we're using these, we're looking at the delta H for each individual thing. And we see that this is going to be ammonia, this is going to be our methane, and then this is our hydrocyanic acid. And so when we look at these are basically their heat of formation of each one of these. Now, hydrogen doesn't have one because it basically is 0 because it's in its natural state. So to use Hess's law, it's just products minus reactants. So our delta H is going to equal our products, which in this case is just our hydrocyanic acid, which has a positive 270.3 kilojoules of energy, minus our reactant, which in this case is ammonia, which is negative 91.8 kilojoules, plus our other reactant, which is going to be our methane, which is negative 74.9 kilojoules. And we go ahead, and since this is minus a negative, this becomes positive. And we add those to it, and we get a delta H value of 437 kilojoules. Looking at this problem, it says calculate the delta H for the reaction. Remember that we have to look at our products minus our reactants. The one thing to keep in mind here is that you have coefficients of 4 and 6 when dealing with our nitrogen monoxide and our water, and then also a coefficient of 4 for our ammonia, and it's products minus reactants, and we should get a value for this of 3,244 0.8 kilojoules for our delta H value. Moving on to the conservation of energy, it says which of the following could be the enthalpy of reaction for the combustion of our C2H6, which is ethane. And so when we talk about a combustion reaction, there's a large amount of heat that is given off from a combustion reaction, and so is going to be exothermic. And so an exothermic reaction is going to have a negative delta H value. So a delta H value that is less than 0. Describe an endothermic and exothermic both on a molecular and a macroscopic level. An endothermic reaction is an energy that a reaction that requires energy, whereas an exothermic reaction is a reaction that gives off energy. An endothermic reaction is going to form more bonds than that are broken. Exothermic reaction is going to break more bonds than those that are formed. Sketch a graph of an exothermic reaction. So an exothermic reaction, when we set up a graph, we'll have our energy diagram where we have energy, and we see that we'll start off exothermic very high, and here, and then go down, and then level off. And so we'll have our delta H value. It will obviously be negative. We see that the energy will have gone down.